Hey, here we go again. What are we doing? Well, we're doing related rates questions, but this time with trig functions. So if you remember back in the calculus of parametric equations, we introduced the idea of if the parameter is t for time, then we would be looking at related rates of change of two quantities with time, and how you can work out one from the other. Do you remember it? Well, here we go again. We're going to have a go this time with the trig functions. Let's look around the screen. So we're going to do this one in a minute. If this is rotating here, over here, and at a certain rate, that theta, how quickly does this go down here? It could be a searchlight coming across a wall or something like that. How fast is it moving? And over here, the idea that if again theta is changing, then how quickly is xy changing, that sort of thing. Down here, if we're rotating A around this flywheel and B is driving a piston, something like that, what are their relative speeds or rates of change with time? Oh, and here's another one. It looks like this is filling up with fluid here. And maybe how quickly is theta changing, or how quickly is the depth changing in terms of filling up this area, so this volume here. So there's lots of practical problems, and it's exciting stuff. So let's get started, and I want to start with just a little bit of revision now here, and this came from an earlier presentation. What is the method of solution? And here we are. We make a mathematical diagram, which you might remember involved drawing a mathematical model, which involved drawing a diagram, labelling it with all the given information, using pronumerals for quantities that vary. Okay, all that stuff that we did before. So you need to go back to the last presentation in the calculus of parametric equations to have a look at that. Anyway, so let's have a look. What's the process? Okay, your process then is to identify the variables of interest, find a formula connecting them, introduce the rates of change by differential calculus, find the derivative, and then evaluate at the particular instant in time. Okay, so the formula connecting the quantities, we might just add something here. It really shouldn't have any other variables. Eliminate other variables so that you've just got those two. Okay, so that's important. Okay, I might just have a look at that again later on now. So what we're going to do is have a look at this process with some screen clippings from Hayes and Harris publications, so it'd be good to have their specialist book there. Before we do that, we have a checklist from there, which is saying you've got these basic tools. Pythagoras' theorem, similar triangles, where we're connecting triangles by the transformation of enlargement. You're getting ratios of corresponding sides are in proportion. That's an important one. And now we're particularly going to have emphasis on these, where the quantities involved can be best connected with sine, cos or tan, and you're going to use things like SOHCAHTOA, right angle triangle trigonometry, and the sine and cosine rules. So now that we've learned how to get the derivative of sine and cos, we can do this type of problem. So it's just an expansion of the related rates we did before. Let's have a look at some of those Hayes and Harris examples. Okay, so we're given this triangle here. Triangle ABC is right angled at A. Check the triangle and make sure all the given information is on there. AB is 20, and it looks like that's a constant, so you can label that there. The angle ABC, got to use a pronumeral here because it's varying at a constant rate of 1 degree per minute. At what rate is BC changing? So there, introduce a pronumeral here because it's a variable. Okay, and so we put those things up here and start the problem off, clearly describing what those introduced pronumerals mean. Okay, now I like people to try and set it up like this. Given what rate of change is given, d theta by dt is 1 degree per minute, and we want to find dx by dt at ABC at theta equals 30 degrees. And what we're going to try and do is connect theta and x, the two variables of interest, and then we're going to differentiate. So you can see here, it's just SOHCAHTOA. The cos of angle theta is the adjacent over the hypotenuse, and that nicely connects theta and x. And we can write it like this so that we can actually differentiate it. So the derivative of cos is minus sine, and don't forget it's a derivative of theta with respect to time. That's implicit here. And then neg 20x to the neg 2, the x to the n rule here with respect to x, and then the derivative of x with respect to time. Okay, so we've got our relationship. Now we want to evaluate, differentiate it. We've done that. Now we want to evaluate at the particular point. It's at theta equals 30. So find the cos of 30 is 20 over x, and we can actually rearrange it to get 40 on root 3. And now we're going to have to use our rates of change in radians. Okay, because the radian measure is a measure that's easy to apply calculus to. Delta theta on delta t, rather than in degrees, we've got pi on 180 radians, because 1 degree, of course, is 1/180th of pi radians there. Okay, so if we then substitute all these in, okay, we get this, and therefore we can rearrange to get the dx by dt. So what that's saying is it's increasing gradually as theta increases there, and at 30 there's the number of units per minute, and because the lengths in this figure are in centimetres, they are the lengths for that rate of change there. So just have a look over here. I've drawn a diagram for that particular instant in time. So it's pretty standard stuff now. The only difference is up here we've got relationships with cos, which when differentiated will be minus sine. Okay, do you get it? Let's do another one. And here's a good statement. We should make that statement at the end. And they said, how is BC changing? BC is increasing because this is a positive rate of change at that many centimetres per minute. And really, we should round this off. In this course, we generally have a rule that it's 3 significant figures, okay? So we'll have approximately that. All right, what about another example before having a go? So here a searchlight S is shines on a vertical wall, okay? So it's there and is located 50 metres from the wall. The light beam rotates clockwise at 3 revolutions per minute. How fast in metre per second is the beam moving on the wall when it's directly opposite the wall at X and 100 metres along the wall at Y? Okay, so you need a very important practical problem, because if you're trying to escape out from behind this wall and you're running down there, oh, how fast do you have to run? Pretty fast, I think. I think the answer to this is pretty quick. Anyway, that sort of thing. But why would you be trying to escape in the first place? I don't know. What are you doing in there? All right, so let's have a look at this problem, and we need to do the diagram now. So here's our diagram, a mathematical model. So we've got theta, we know its rate of change, and we've got x for the distance Lx, okay? And this is swinging around this way. So what could we do here? We'll come over here, we could say here, given what, d theta by dt, and it's rotating clockwise at 3 revolutions a minute. Now clockwise is negative, so it's neg 3 lots of 2 pi radians in 60 seconds. So we'll use neg pi on 10 radians per second. Okay, you could leave it as minutes, but let's use seconds here because I think it says, oh yes, in meters per second. Okay, so it asks us for those units now. So we have to find how quickly it's moving down the wall, dx dt, or across the wall, sorry, dx by dt at 2 points. So we want, just put this differently, dx by dt at x and also at y. Okay, they have two particular cases here we want to work with. So now we're going to connect the two quantities, x and theta, and then we'll differentiate. So let's look at the diagram, and you can see here now, so we've just done that calculation there, that the tan of theta is, we'll use this one, opposite over adjacent, so that's a good one to use. One unknown only, we wouldn't use SL with the hypotenuse there, because that would be another thing that was unknown, so we don't want that. So here then we've got our relationship. What's the next step? Get the derivative, so that's sec squared, and just remember theta is varying with time, d theta by dt, and then the derivative of x150 or 1/50th x is the constant, 150 times dx by dt. And now we've got to look at the particular cases. If L is at x, what do we know? Well, theta is 0, x is 0, and the cos of 0 is 1, and the sec therefore is 1. Sec is, remember sec theta is 1 on cos theta. So, subbing them in, we've got those, and we can rearrange that to get neg 5 units per second. And what are the units? Well, 50 was in meters up here, so any lengths now in this problem will be in meters. We changed it to per seconds, so that's that. So therefore, it's negative, so it's decreasing at 5 meters per second, 5 pi meters per second at this instance, because Lx is getting less, that rate of change is negative. 5 pi meters per second, you're going to have to run faster, dodge that light. Right, what's pi? Approximately 3.142 times 5, 15.5, 15.6 meters per second. Wow. Okay, let's have a look at the other instance. L is at y. How far is y? Well, we're told earlier it's 100 meters. Okay, so here we can put in our values now in our rates of change down here, but we've got our pi on 10, but now we know x is 100, so tan theta is 2, so we can find here, put theta in a triangle, the tan is the opposite over the adjacent, so by Pythagoras we can do that. We don't have to go with technology and find that angle in radians as such at the moment. We'll do that in a minute. Here, well, we don't actually have to do it, so here the cos of theta is the, here we are, just get rid of that, is the adjacent over the hypotenuse, worked out with Pythagoras, so therefore sec is 1 on cos, which is 1 on root 5, which is root 5, and square it is 5. So now we can sub in, there it was there, sec squared, the rate of change for the angle, and so on, rearranging it, it's 25 meters per second, 25 pi meters per second. So the illuminated spot is moving at 25 pi meters per second, and so it's speeding up there along that wall, but the theta, the angular rate of change there, the angular velocity, is still that constant. So it's the same thing as what we saw before. Further out on the arm, it's going to be moving more quickly. Okay, let's have a look at some problems now, and just check that you're going through the procedure. Okay, you need a diagram, a good model, so that's a diagram. And generally in tests and exams they give them to you. Here for this first batch there aren't any diagrams, so you want to construct it carefully. All the given information on the diagram, introduce pronumerals for anything that's varying. Don't put constants in unless it's constant throughout the problem. Get the relationship, differentiate, so you've got a differential equation there. Okay, so pause presentation, have a look at those four. We've got the answers or the solutions down below. Let's have a look at question 5 now. 5, 6 and 7. Okay. Pause it and have a look. You probably have to do most of these, get some skills up. And question 8 is that piston problem. Just come up a bit here. That shaft driving a piston or something here at B. This is a flywheel. Okay, and then the problem here about the water trough. That's a good one. Scratch your head about that one. And here's a hint down here. Okay, so you might play with that a bit. You must know your work. I'll write that down now. You must know your work. Know what you're trying to do. You still have to solve the problem. See what I'm saying there? It's different, isn't it? Knowing your work means you know a strategy for solving the problem. You know approximately where to start. Then you've still got to be able to do it. Okay. All right. So let's come on down now and look at the answers. So 7C question 1. And then let's look at 2. A and B. And question 3. Question 4. Just see the whole of question 5 here. Okay, question 5. And question 6. Question 7. Question 8A, we've got more to come there. And there's B. Go to question 9 now. A. We'll just come to B. Come down a bit more. Okay, so there's B. Well, what I want to share with you is please know your work and be confident, and then when things get a bit messy with sines and causes and stuff, you will be able to work through it. But you must know what you're trying to do and be confident in that. Okay, so you stick to it as things get a bit more algebraically not nice. Okay, all right, so we'll be doing more of this, of course, with the calculus of trig functions, and later on what we're going to be doing is to be integrating them. So in the next presentation, that's what we'll be up to. So it's cheers for now. Catch you later.